Okay, to finish chapter 2 notes, we need to talk about a few more things regarding motion. So one is time interval. Time interval is, we're going to use delta t to represent change in time. That's time final minus time initial to get change in time. Displacement will be delta d for change in distance. Distance final minus distance initial. And we're going to be making some position time graphs. So here's an object that as time goes on, it's moving forward. And the slope's constant, so that's going to be a constant rate, because the slope here represents rise over run. So we're talking about when we have time on the x-axis and distance or position on the y-axis, our rise over run is always going to be in meters per second, which is a speed. So our slope is a speed. And in this case, it's not changing, so it's constant. All right. So the question is here, when did the runner reach 30 meters beyond the starting point? So the question is, when does the runner reach this point? It looks like if you drop that down at about 6 seconds. Okay, a couple more questions, or one more. Where was he after 4.5 seconds? Well, 4.5 seconds is about here. If we trace that up, it looks like they were at about 20 meters. Approximately 20 meters. So reading graphs is going to be important. Let's try more with average velocity this time. Average velocity is defined as the change in distance over the change in time. Okay, you might have remembered this formula, velocity equals d over t, or maybe you use distance equals rate times time. Well, this time our rate is velocity. So instead of using r, we'll use v. You divide both sides by t, you get this equation, or this equation. It's just change in distance over change in time. Okay. So here's a graph. Same graph. And you can see that the average velocity then would just be that change in distance. So we could pick 2 points. Let's pick this point here, and maybe this point here. Looks like the point 1,5 and the point 3,15. So 1, 5, and 3,15. We can just find the slope, right? The change in distance is y2 minus y1, 15 minus 5. So we have rise over run, or slope. y2 minus y1 divided by x2 minus x1, 3 minus 1. This gives me 10 over 2, which is about 5 meters per second. The units on the rise, the difference in the y values in this case is in meters, and the difference in the x values is going to be seconds. So our answer is 10 over 2 meters per second, or 5 meters per second. That's our average velocity in between these 2 points, which in this case, since it's constant velocity with a straight line, that's our velocity overall. All right, instantaneous velocity is different than average velocity. The speed and the direction of the object could change at a specific time. All right, so here's an object that over time it gains position, and then it seems to slow down, comes to a stop, and accelerates again, and gains more position. We can ask some questions about it. For example, what's the instantaneous velocity at 1 second? Well, instantaneous velocity at 1 second. Well, we don't know that. Okay? We don't know what the instantaneous velocity is at 1 second from this graph. We know we could find the average by doing this point and this point and finding the slope. That's not quite the instantaneous velocity. The instantaneous velocity is the slope at that point. Actually, it's the tangent line there. So we could draw that tangent line in and guess. It looks like it goes up about, from 1 to 2, looks like it goes up about 5 meters in about 1 second. So it looks like it's about 5 meters per second if we do rise over run. So it goes up about 5 meters in about 1 second. So we can guess with an approximation of a tangent line there, but we don't know the actual instantaneous velocity unless we want to get into some calculus and take the derivative of this function, which we're going to wait on that. Next question, what's the instantaneous velocity at 4 seconds? Well, at 4 seconds, it looks like if we draw a tangent line in there, it looks like the velocity is 0. It looks like the rise over run for this point is 0 over some run, which in this case is just 0 meters per second. So it looks like it's not moving at that point. All right. The next thing is, what's the average velocity? Well, the average velocity over this time interval, it depends what interval we want, but if we're going to go from 6 seconds, then we have these 2 points. That would be our average velocity right there if we use those 2 points for slope. In which case, one of those points is 0, 0, and the other point is 630, So average velocity would be y2 minus y1, which gives us 30 over 6, or about 5 meters per second. It turns out this average velocity was similar to the instantaneous velocity at 1 second. As you can see, those slopes look like they're about the same. Okay, the last thing I want to share with you is our equation for motion. It's our first equation for kinematics that we're going to use besides our standard velocity equation. Its position d equals the average velocity times time plus the initial distance. Okay, comes actually right from the same equation. We rearrange it, velocity equals change in distance over change in time. So if we rearrange this and just call it distance final minus distance initial and solve for distance final, we'll get this equation. Okay, it looks familiar. It's a line, right? It's got a y-intercept, a starting distance, initial distance. It's got a slope, which in this case is the rate for velocity, and it's got two variables, independent and dependent variables. So we're looking at our linear equation then for distance, and the graph would look like this. So we'll try some of these problems in the homework, but for now I hope this helps.